Welcome to the e-learning course 1, lesson 1, session 1.3. In this session, we'll focus on alternative risk measures when observations are not normally distributed. The learning goals for this session are: you know the deviations from normality and what alternative risk measures can be used. You should be able to analyze and interpret historical returns on risky portfolios, and students should be able to deal with normality and long-term investments. Normal versus non-normal distributions. As we noted in the previous session, normality of excess returns hugely simplifies portfolio selection. Normality assures us that standard deviation is a complete measure of risk, and hence the Sharpe ratio is a complete measure of portfolio performance. Unfortunately, deviations from normality of asset returns are potentially significant and dangerous to ignore because standard deviation and the Sharpe ratio are not anymore complete measures. To determine non-normal distribution, skewness and kurtosis need to be considered. Normal and skewed distributions. As a measure of asymmetry, called skew, is the ratio of the average cube deviations from the sample average, called the third moment, to the cubed standard deviation as shown in the formula at the bottom. So now let's compare the black and blue skewed curve with the gray normal curve. When a distribution is skewed to the right, as is the black curve, the extreme positive values when cubed dominate the third moment, resulting in a positive skew. When the distribution is positively skewed to the right, the standard deviation overestimates risk, because extreme positive surprises, which do not concern investors, nevertheless increase the estimate of volatility. When a distribution is skewed to the left, as in the blue curve, the cube extreme negative values dominate and skew will be negative. So that means, and more importantly, when the distribution is negatively skewed, the standard estimation will underestimate risk. Normal and fat-tailed distributions. Another important deviation from normality, called kurtosis, concerns the likelihood of extreme values on their side of the mean at the expense of a smaller likelihood of moderate deviations. Graphically speaking, when the tails of a distribution are fat, there is more probability mass in the tails of the distribution than predicted by the normal distribution. That extra probability is taken at the expense of slender shoulders. That is, there is less probability mass near the center of the distribution. Although symmetry is still preserved, the standard deviation will underestimate the likelihood of extreme events, large losses as well as large gains. Looking at the formula, kurtosis measures the degree of fat tails. We use deviations from the average raised to the force power scaled by the force power of the standard deviation. We subtract 3 in the equation because the expected value of the ratio for a normal distribution is 3. Value at risk. The value at risk is a commonly used risk measurement tool. It is actually written into regulation of banks and closely watched by risk managers. It is the loss corresponding to a very low percentile of the entire return distribution. For example, the first percentile return. When portfolio returns are normally distributed, the value at risk is fully determined by the mean and standard deviation of the distribution. Recalling from the previous slide, the minus 2.33 is the first percentile of the standard deviation distribution with mean 0 and standard deviation equal to 1. The value at risk for normal distributions is shown as in the formula below. The mean minus 2.33 times the standard deviation. To obtain a sample estimate of value at risk, we sort the observations from high to low, and the value at risk is the return at the first percentile of the sample distribution. Lower partial standard deviation, also called LPSD. The use of standard deviation as a measure of risk when the return distribution is non-normal presents two problems. First, the asymmetry of the distribution suggests we should look at negative outcomes separately, and second, because an alternative to a risk portfolio is a risk-free investment, we should look at deviations of returns from the risk-free rate rather than from the sample average, that is, a negative excess return. A risk measure that addresses these issues is the lower partial standard deviation called LPSD of excess returns, which is computed like the usual standard deviation but using only bad returns. Specifically, it uses only negative deviations from the risk-free rate. Sortino ratio. Practitioners who replace standard deviation with the previously discussed lower partial standard deviation typically also replace the Sharpe ratio, which is the ratio of average excess return to standard deviation, with the ratio of average excess returns to the lower partial standard deviation. This variant on the Sharpe ratio is called the Sortino ratio, as shown on the slide. Historic returns on bills and bonds. We can now apply the analytical tools worked out in previous sessions to look at historic performance between 1926 to 2015, comparing Treasury bills and Treasury bonds in the two graphs below. We would assume that T-bills are widely considered the least risky of all assets. There is essentially no risk that the US government will fail to honor its commitments to these investors, and their short maturities means that their prices are relatively stable. Long-term US Treasury bonds are also certain to be repaid, but the prices of these bonds fluctuate as interest rates vary, so they impose meaningful risk. Comparing the two graphs, it confirms that Treasury bonds have greater volatility compared to T-bills. Compared to T-bonds, the distribution of T-bills returns is far more concentrated in the middle of the distribution with far fewer outliers. Historic returns of equity. Analyzing historic returns of common stocks, this asset class is considered the riskiest compared to T-bill and Treasury bonds. As a part owner of the corporation, your return will depend on the success or failure of the firm. These assumptions are also confirmed in the graph below. Stock returns are much more dispersed, less concentrated, in the middle, and with far more outliers. Historic returns on risky portfolios. The previous graphical conclusions about risk and returns comparing T-bills, T-bonds, and stocks can also be numerically confirmed in the table below. it becomes evident that average returns, risk premiums, standard deviations, and outliers have been highest for stocks. And as previously assumed, T-bills have been the least risky and have generated the lowest average returns. Historic returns around the world starting from 1900 to 2015. On the next graph, average excess returns in 20 stock markets have been analyzed from 1900 to 2015. The mean annual excess return across these countries was 7.4% and the median was 6.5%. You should ask yourself the questions when analyzing long-term historical track records. First, do economic factors that prevailed over that historic period from 1926 to 2015 adequately represent those that may prevail over the forecasting horizon? And second, is average performance from the available history a good yardstick for long-term forecasting? Short versus long-run risk. Continuing on the two questions raised on the previous slide, it is important to differentiate between short-run versus long-run risk. Our result on the risk and return of investments over different time horizons appear to offer a mitigation of investment risk in the long run. Because expected return increases with horizon at a faster rate than standard deviation, the expected return of long-term risky investments becomes ever larger relative to its standard deviation. Does this mean that investments are less risky when horizons are longer? You should know that investments in risky portfolios do not become safer in the long run. On the contrary, the longer a risky investment is held, the greater the risk, as the probability of shortfall is a poor measure of the safety of an investment. It ignores the magnitude of possible losses. We are at the end of session 1.3. After having carefully studied the slides and the relevant chapters in the book, please start with the review questions.